Okay, yes, here we go. Chemistry time. Today we're talking about the gas laws. Let's do it in teal. I think I always call it so. Let's just call it chemistry of gases. Gases can be spelled either G-A-S-S-E-S or G-A-S-E-S as a matter of interest. The ones that should be reviewed, that we should remember, there's actually quite a lot of this that's review. As we've been finding out all year, chemistry is very iterative. It builds upon itself. There's a lot of things that we see repeat or reiterate. One thing that you should remember from physical science are the three kind of proportionality gas laws, and there's a combination of those. So let's talk about those real quick. So the first one we have is Boyle's law. Initial pressure times the initial volume equals the final or second pressure times the final volume. That is, in words, we might say, if temperature is held the same, right? Temperature is not part of this equation. If temperature is held the same, as the pressure on a gas increases, the volume of it decreases. More pressure exerted on it, more lower volume. Pressure up, volume down. They're inversely proportional. The next one is Charles' law. Volume 1 over temperature 1 equals volume 2 over temperature 2. Another interesting spelling or syntax thing. Charles, spelled like this with the apostrophe after it, is pronounced as Charles. You know the word Charles already has an S in it. So if you want to make it possessive, there's two ways. Either put the apostrophe afterward and you still say Charles, or Charles's would be like this. And both are actually correct in English. There are nuances to that, but both are correct. And then the final one is Gay-Lussac's law, which is pressure 1 over temperature 1 equals pressure 2 over temperature 2. And this one, as the pressure is increased, temperature increases. Both of these two are directly proportional. Oops. I forgot to mention in Charles' law, when the temperature on a gas, if pressure is held the same, right, pressure is not part of it. If pressure is held the same, if we increase the temperature of a gas, its volume also increases. And similarly with Gay-Lussac's law, if the temperature on a gas is increased, its pressure will increase if volume is held the same. They go up together or down together. And there are other ways to think about it. The common way for this one that I like to think about is if we have one of these. You've seen one of these before? This is an aerosol can. This one happens to be Dust-Off brand electronics compressed gas duster. Other brands are available. But you know, if I release the pressure of this, it's going to feel like what? What temperature is it going to feel like? Cold. And sure, it does, because the pressure is going down, right? It's very pressurized in here. As I release the pressure decreases, and therefore the temperature decreases too. The inverse of that one is if you have like a bicycle pump, a lot of times you'll notice that the pump, whether it's an electric air compressor, you might have a gas-powered air compressor, or a hand pump, the cylinder of that will get warm. And a lot of times people think that's from friction. It's not. It probably is a little bit. In fact, I would say it definitely is a little bit. But mostly it's what's called adiabatic heating. It's the heat increase due to pressure increase. So as we put more pressure on something, its temperature increases. So in that case, pressure down, temperature down. In the case of the bicycle pump, pressure up, temperature up. So these two are both examples of directly proportional. As one quantity increases, the other quantity decreases. And this one is an example, Boyle's law is an example of inversely proportional. As one increases, the other decreases. So those are the three basic proportionalities of gases that describe their behavior relating to their temperature and pressure. There is a combined form, which is, if you just memorize this one, you can always use it. P1V1 over T1 equals P2V2 over T2. This will work for every problem, you just don't use the one that you don't have. And what's nice about the combined gas law, We can use it in every situation where there's pressure and temperature. And if the pressure or temperature both change, we can see how the volume changes. We might need to do some little bit more complicated math, but it can be used in that way. Two things to remember. Temp must be, I'm going to put in an absolute scale. Both because I think that'll remind you why it has to be that way, and it will include other scales besides Kelvin. I'm going to put in parentheses though, like Kelvin. The Kelvin scale, abbreviated K. Because since the Kelvin scale starts at absolute zero, there are no negative numbers. The coldest temperature in the universe that can possibly exist is zero, and so there can't be negative numbers. That's why we always use it for these, because throwing a negative number in here, we might end up with a negative pressure, which is impossible, or a negative volume, which is impossible. So we have to use scales that don't have negative temperatures too. The other absolute temperature scale that I'm aware of, at least, is the Rankine scale, which is like Kelvin in that it starts at absolute zero, but it goes up in Fahrenheit increments instead of in Celsius increments. And then I'm going to put in parentheses here, degrees Celsius plus 273.15 equals Kelvin. That's the basic math. If you get a temperature in degrees Celsius, which was very common, maybe even more common than Kelvin for these problems, you just add 273.15, and that's the Kelvin temperature. So that's one rule. Temperature must be in the absolute scale, and I'm going to put 1. And 2, the units for, well, I was going to put for pressure and volume, but really for all of them, pressure, volume, and temperature must match. I'm going to put that in quotes. But basically, if pressure is in atmospheres, it has to be in atmospheres for both 1 and 2. If volume is in liters, it has to be in volume, or it has to be in liters for both volume 1 and 2. You can't have volume in gallons here and volume in liters here, or you have to do a, if not, what? What's our solution? Convert. We do a unit conversion, and you have to show that. So, for instance, if we were given 4 liters of gas at 98 degrees Fahrenheit is how many gallons of gas at 150 degrees Fahrenheit? Well, we would have to point 1, we'd have to change our temperature from Fahrenheit to Celsius, and then Celsius to Kelvin. And then, since we want the answer in gallons, and we were given it in liters, we would have to convert this volume to gallons. So there are unit conversions nested in there. That's one of the things I meant at the beginning when I said that science is iterative. We have to know how to do unit conversions successfully, which we learned not only at the beginning of this year, but also in physical science. We have to know how to do those successfully in order to get our correct answer. And we have to be able to have our correct temperature scale too. I think that's pretty much all I want to or am going to say about the proportionalities, the temperature proportionalities. And one of the reasons for that is that we did do it in physical science. And the other reason is that I think this is pretty simple math. I think we're going to be able to easily use these, especially as we start working or as we continue working on them. They'll become very apparent how these work together. Having said that, do you have questions? Or we're going to move on to part 2. There are 2 more things to talk about. This was number 1. There are 2 more parts. The first was these proportionalities. Do you have all of this written down? Or? Yeah. Okay. If you're watching this online, like if you're in the afternoon class, for instance, I'm talking right to you, afternooners, will. You can pause it and re-look at all that stuff. The second thing we're going to talk about is what's called the ideal gas law. I'm going to change colors so that it can symbolize a change in our minds. Ideal gas law. An ideal gas, conceptually, one of the reasons we use the word ideal is because it's a non-actual gas. In reality, because of friction and various other intramolecular forces, which we learned about, intermolecular forces that we learned about in the last chapter, an ideal gas doesn't exist. But the idea of an ideal gas is that the atoms, when they collide, do so without any loss of energy. They just have a perfect collision, what we call, remember in physics, an inelastic collision. No energy is lost. They just totally bounce. In reality, that doesn't happen. There is friction. There are intermolecular forces. But they are so minuscule that we can effectively use what's called the ideal gas law mathematically, with the understanding that in reality it wouldn't function exactly the same way, but mathematically it can be shown that this is the case. And math is great for things like that. We just actually this morning in earth science were talking about ellipses, because in reality, all planetary orbits, if you remember from physics, are ellipses, because a perfect circle doesn't exist in nature. But in math, a perfect circle does exist, and it's actually much simpler. Math tells us that simplicity is perfection, basically. I mean, there's a lot of other things that math says. Even something as basic as like 1 apple plus 1 apple equals 2 apples. Well, in reality, the first apple might weigh a little bit more than the second apple, and so you don't actually get 1 plus 1 equals 2. You get 1.003 plus 0.894 equals whatever that equals. There's always imperfections in reality, but math is very almost spiritual in that way, that it deals with the perfection of nature. And so the math for this is PV equals nRT. That's our equation, where P is, can you guess? Pressure. And we'll talk about what they're measured in a second. Capital V is volume. N, lowercase n, is amount of gas. I shouldn't even have to put of gas, because otherwise I would have had to put that for pressure and volume too. So N is amount. R, very interesting, is the ideal gas constant. And capital T, you know, temperature. The ideal gas law can be used excuse me, because of something called Avogadro's principle. Remember, Avogadro's number was 6.02 times 10 to the 23rd. This guy did a lot of work with the physicality of chemistry. He was very good at applying, apparently, very good at applying math, that almost spiritual ideal, to the reality of chemistry, what we might call today physical chemistry. And we use what is called Avogadro's law, equal volumes of gases at the same temperature and pressure have the same number of particles. Basically, no matter what it is, because of the way gases inelastically collide, because of the way they perfectly, remember ideally, because of the way they perfectly bounce off of each other, it doesn't matter what the gas is. Carbon dioxide, sulfur hexafluoride, helium, oxygen, doesn't make any difference. As long as it's a gas, the same volume of that gas will have the exact same number of molecules because they behave ideally. So unlike liquids and solids, where something with the particles closer together would be denser than something with the particles farther apart, in a gas, since they behave ideally, no matter how much they weigh, they will fill the same amount of volume under the same temperature and pressure conditions. Now again, in reality, that's not quite true. Heavier gases tend to have a little bit more friction, lose a little bit of energy, and so they tend to be just a little bit denser, but not in a way that is as severe as you would expect when we normally talk about the difference between like Newton's laws and reality, right? Where friction made a huge difference. In this, it changes it from like 22.4 liters in a mole to like 22.21 liters in a mole. And so it's a pretty small, not insignificant, but low significance difference. These values then relate to the volumes of gases at the same temp and pressure, right? Equal volumes of gases at the same temperature and pressure have the same N number of particles, okay? We can use, depending on what we use for R, your book provides on page 454. Can you see the screen to see if that's showing up? I never do this right. Is that little table on there? Table 13.2, can you see it? Up and to the left like that? Okay. You can pause it on that frame if you're watching and you don't have your book. Ooh, that was close. That made me, almost made me scared to drop my book because that would be bad. But there are, depending on what the values of R now sounds like I'm just a seal. Depending on what the values of R are, we use different units. Basically, the units we use for these are determined by which value of R we want to use. So the most common one is listed there first on the table. It's 0.0821. Where's my R? 0.0821. So kind of like some of the things we had in physics, not only do we know the unit, it has an actual value. It's a constant, so it has an actual value. Something like the universal gravitational constant, the electrical constant, those things that we talked about in physics have an actual value that stays the same. 0.0821 liter atmospheres, so liters times atmospheres per mole Kelvin. Moles times Kelvin. And guess what? If we use this one, 0.0821, guess what the pressure has to be in? Atmospheres. You see why? Because we have that in our unit down here. Volume must be in liters, amount must be in moles, that's always true, and temperature must be in Kelvin. Other options are liter kilopascals per mole Kelvin. So if we had our gas in kilopascals, we wouldn't necessarily have to convert to use this, we would just use a different value of R. And then the other option on here is liters millimeters of mercury per mole Kelvin. So if the pressure were given in millimeters of mercury, we could just use a different value of R instead of having to convert that pressure. I would say if you are going to memorize one of the R's, this is the best one. It's easier to memorize this value of R and then convert your pressures instead of memorizing all three of them. That's just, I mean, that's kind of just preference. In either case, you're memorizing 4 different things, so. To use this, we use it just like any equation, except you'll notice that there's 2 variables on this side and 3 on this side, so we're always going to have to manipulate it. So we're always going to have to manipulate it, that's one thing. And then, of course, we just substitute. Equation, manipulation, substitute, solution, just like you're used to doing. 2 kind of corollaries that come out of this, without going too in-depth into the way they are derived, are that the molar mass of a gas is equal to its mass times R times its temperature divided by pressure times volume. And you can, I hope, kind of see how we use this amount here to derive out mass and molar mass. So we can, this becomes a useful, I'll just add the ones that we don't have yet. Capital M in this case is molar mass, measured in grams per mole. And of course, lowercase m is just mass, in this case measured in grams. How we've kind of substituted out, that's not the word I really want to use, how we've swapped out having straight up amount in moles for being able to calculate molar mass by just adding in the mass of the gas also. And then finally, another thing that we can get out of this is the density of the gas, which your book uses capital D for density, totally fine. I'm going to, again, use the Greek letter rho because I think it makes me look fancy, is equal to the molar mass times the pressure over R, that constant R times the temperature. I really could have drawn, and now I realize this, I really could have drawn this arrow. It's not so much that these are both corollaries of this one, it's that this one is a corollary of this one, which is a corollary of this one, and we end up with the density of a gas. Rho is density, measured in grams, in this case grams per. Must be milliliter, let me check. No, it would end up being liter, grams per liter. And that makes sense because that's the normal unit for gas density. Because gases have very little mass per unit of volume. So now, basically what we've done is we've see how, you remember from the beginning of the year, M over V is density, right? So we've taken M divided by V, which is density, swapped that over, and rearranged it to get this. So now we have a way, if all we know is R, which we always know, the temperature and the pressure of the gas, and its molar mass, we can find its density. Really, I will tell you, remarkably easy math for being able to just look at, like we could really just have, let me think of a gas, xenon hexafluoride, right? That's one we've talked about in the last video too, I think, but very rare substance, but we can mathematically find what we would expect its density to be at any normal or at any pressure and temperature using just its formula, right, to get the molar mass, and this value R that Avogadro derived. So it's a really powerful tool. All we need to know about something that really exists in nature is its formula and the conditions it's in, and we can tell its density also. Conversely, if what we know about it is its density, which we could measure in a lab, and the pressure and temperature, which not only could we measure in a lab, you could probably measure that in your car. If we only know those three things, we can pretty easily, we couldn't quite find its formula, but we could find its molar mass, which would be very, very, very valuable to us. So it's a really powerful tool, these equations are, to allow us to learn about our world. So those three equations are part 2. And we will do example work with those as we work on our chapter reviews. Questions about that before we move on? Good? Kind of, this is reminding you of physics probably. This is the kind of stuff we would do in physics all the time. Get back into that. That's a great way to say it. Dust some cobwebs out. Now I'm going to make you shift gears back to chemistry, because the next thing we're going to do, and the final thing for this lesson, is gas, our best friend, coming back almost with a vengeance, gas stoichiometry. And I love this one. This might be my favorite thing in all of chemistry as far as the math of chemistry, because it's just, this will be my opinion, but it's just such a neat little condensed way of showing almost everything that we've done in chemistry class up until this point, including what we just did. And more than that, it is what I just said, but it's extremely simple. It's very elegant, and the elegance comes from this. At STP, which we'll talk about in a second, 1 mole of ideal, I'm going to put that in parentheses, they all behave mostly ideally, equals 22.4 liters. So all of what we just talked about, and all of what we learned about in stoichiometry, and even what we learned about last chapter about the intermolecular forces, comes down to this line. And because we've built it up so much over the course of the year, unit conversions, bonding, naming, writing formulas, learning stoichiometry, learning about the mole first and then stoichiometry, intermolecular forces, gases, because we did all that complex work to begin with, we can reduce it all to this line, this very powerful line, and because it has all the weight of those bricks we use behind it, it's a very, very heavy line that will do a lot of work for us. The things we need to know are that standard temperature and pressure are 273.15 Kelvin, which is 0 degrees Celsius, and 1.0000 infinite atmospheres. This is an exact number, so infinite sig figs. And then this we pretend has infinite sig figs. So at standard temperature and pressure, which is these conditions, 1 mole of an ideal gas, the lighter a gas is, the more ideally it behaves, takes up this much room. Very powerful, because now we can convert from an amount in grams of a gas, or even molecules of a gas, that is to say particles of a gas, to its volume in liters. And I think, even though I normally like to have you do the examples kind of outside of the discussion, I don't think it's a useful thing for everyone to see when they're watching the video, because you can have your own examples. I think the best way to show this would be an example. And so, let's say we have, at STP, we have 1.3 grams of, can you give me an example of a gas? Yeah, just some gas on nitrogen, good. So 1.3 grams of N2, and we want to find the volume of that. Well, all we have to do is just a conversion. 1.3 grams of nitrogen. We're going to go from, can you guess? Yep, grams of nitrogen to well, we know this. We know we want to find its volume, and we know that its volume has this amount. Well, it will be in a second, but for now we're just going to go from grams to moles of nitrogen, and then moles to liters. How do we find how many grams are in 1 mole of nitrogen? Well, it's this. 14.007, this is from the periodic table. Grams per mole, there are 2 of them. So N2 will be 28.014 grams per mole. 1 mole of nitrogen is 28.014 grams of nitrogen. And then as with every ideal gas, 1 mole of nitrogen is 22.4 liters of nitrogen. And with the very, very light calculator work, simply typing in 1.3 divided by 28.014 times 22.4, we end up with 1.0, nope, it'll just be, 1.0 liters of nitrogen. So that's sig figs. And this works in reverse too. Like you can imagine a balloon. I'm sure you've seen balloons. If you have a balloon of mostly nitrogen, well, in this case, entirely nitrogen, that has a volume of 1 liter, it weighs this much, which is so handy in the lab because it's very difficult to actually have the mass of a balloon, right? Because what are we going to, could we measure the mass of a helium balloon? It's floating away. Could we even a nitrogen balloon or an air balloon? We can't really sit on a scale because then we're measuring the mass of the balloon because we exist in an environment of air. So this powerful tool allows us to tell the mass of a gas. Very, very useful. And you can see, we have it in this equation, but we could very easily apply this to chemical reactions. This much of a gas. We know this balloon of hydrogen has this volume. How much water is it going to make when we explode it? Well, we could very easily do gas stoichiometry with reaction stoichiometry to tell how much one thing to another. It's just I hope I've impressed upon you what a powerful tool this is and how it really relies on everything we have done this year, from unit conversions to naming to calculating molar mass. All of it kind of comes together. And if you can do this, you can do chemistry. And that's why usually this is kind of the last chapter we do. It's March, so it won't be. But usually I could give you a single question and it would be your test about can you do chemistry. If I just include a polyatomic ion, something that it has to be named, and so much of it is wrapped up in this. Questions? Bye.